Now we're ready to see what those trigonometric functions are and why they exist and what they do. In the previous video, the previous example, we looked at an angle here with some arbitrary line that cut across the angle. The first step here is to actually switch or rotate the line so that it makes a perpendicular with one of the angle sides. In this case, we'll work with the bottom sides. So here I rotated the line and I shifted the points P and Q, remember, to reflect the intersection points. I will again work with parallel lines, so I'm gonna have another line here parallel to PQ. So once again, that line is going to be perpendicular to the bottom side of the angle. The intersection points here are marked P prime and Q prime. We have two corresponding angles here at P and P prime, or I can write them as OPQ has to be equal to OP prime Q prime. And of course, we also have another pair of corresponding angles at Q, but those are really 90 degrees. So when you have this little symbol here of two lines at 90 degrees, we usually use them to mark 90-degree angles in our geometrical problems, or even in physics if you're drawing some geometrical figure here. And we can write those corresponding angles as the angle OQP is equal to the angle OQ prime P prime. Again, we have the similar triangles as before. One orange, small orange, and one blue triangle. Only in this case, we're actually working with right angle triangles. Let me write them. OPQ is still similar to OP prime Q prime, and therefore we still have the proportionalities that we can always set up for any two similar triangles. So for the orange and for the blue, the proportionality ratios are OP over OP prime has to be equal to PQ over P prime Q prime, and it has to be equal to OQ over OQ prime. So let's focus on the first portion here of these proportionalities. And I'm going to write it down here on top of the screen. That means that the side OP over the side OP prime has to be equal to the ratio between PQ and P prime Q prime. Now, if I multiply both sides by the denominators, OP prime and P prime Q prime, what I'm going to have here is OP times P prime Q prime is equal to OP prime times PQ. Now I can divide both sides of this equation by the common denominator OP and OP prime and cancel some terms. On the left hand side, OP will cancel. On the right hand side, OP prime will cancel. So what I effectively did is using algebraic rules to rearrange the terms. This is something students are expected to be extremely fluent and familiar with, and I put it here in details for the first and only time in the class, just to remind you how we do those algebraic manipulations. So after rearranging that original ratio, we have P prime Q prime over OP prime has to be equal to PQ over OP. Now let's see what this means for our triangles. Here is that original angle theta with the point O, and here is the orange triangle OPQ. So for that orange triangle, the ratio of PQ over OP is effectively the side that faces or opposes the angle theta over the hypotenuse of that right triangle, OP. For the blue triangle, of course, I will have the P prime Q prime over OP prime will also be the side that faces the angle theta in the blue triangle divided by the hypotenuse of the blue triangle. And here now you can see why we ever bothered defining the trigonometric functions sine and cosine. It turns out that the ratios between the opposite side and the hypotenuse for each of those orange blue triangles, you can have 1000 or unlimited triangles as long as they're similar. That ratio always is the same for all triangles. and depends only on the angle, or really on the slant between the two originally intersecting lines. And that is how we really define what the sine of theta is. The sine of theta is defined as the opposite side over the hypotenuse in any of those right triangles. Remember, if it's true for one of those right triangles, it will be true for all of the other similar right triangles. Similarly, we can go back to the original proportionalities and work with the second part here, and that will eventually lead to the definition of cosine of theta, which will be defined as the adjacent side over the hypotenuse. So I included this so you can get a big picture and appreciation of the merging of geometry and algebra and physics and to see why things are the way they are. This is not really necessary for you to succeed in physics. So let me summarize the most important findings of these videos. But apart from that, you will be fine by simply memorizing the definitions and being able to recognize when you're working with sine or cosine and how to do it. So let's just summarize here. We saw that the definition of sine theta is going to be the opposite side over the hypotenuse. We also have the definition of the cosine function, which is the adjacent over the hypotenuse. We have two actually more definitions. One definition of a tangent, in which way we work with the ratio between the two sides, not the hypotenuse, but we work with the opposite over the adjacent side. And again, that all comes from those proportionalities from the similar triangles. And we have also the definition of cotangent, which is just the adjacent over the opposite. Now, we rarely write down and work with the cotangent because look at the definition. By virtue of its definition, cotangent will always be 1 over tangent theta. So if you end up having a cotangent in your formulas, you will probably switch very quickly to tangent. And so naturally we end up working with the tangent function most of the time. At least I don't remember in recent past ever using the cotangent function. One more thing here. We have, as far as uh, right triangles, we have the Pythagorean theorem that tells us that the sum of the squares of the sides is going to be always equal to the square of the hypotenuse. So let's look at the orange triangle here for a second. The Pythagorean theorem for the orange triangle means that OQ squared plus PQ squared has to be equal to OP squared. Now let's divide both sides by OP squared and see what happens. On the left hand side here, I will have to distribute, so I'll have OQ over OP squared plus PQ over OP squared. And on the right hand side, I will have some cancellation, so that will be 1. Now let's look at that OQ over OP for the orange side. The OQ is the side adjacent to theta and OP is the hypotenuse. So here I can actually write that this is the adjacent over the hypotenuse ratio squared. The second term will turn out to be actually the opposite over the hypotenuse ratio squared, and that has to be equal to 1. So now you see that if you remember the definition of sine and cosine, you recognize that the first term, adjacent over hypotenuse, is simply the definition of cosine theta. And the second ratio is really the definition of sine theta. So here we arrive at a new way of expressing the Pythagorean theorem in terms of trigonometric relations. You will see this very often in the physics class. We will simply write that sine squared theta plus cosine squared theta is always equal to 1.